Welcome back all of you. In the last class, we started discussing about product operator formalism. It is an approach we use to understand the behavior of the magnetization, how the magnetization is evolving at different time periods of a given pulse sequence. So for this, we started introducing what is product operator, and I said it is based on the density operator theory, and it is given by rho of t at any given instant of time t, and when I know rho of t, I know how the magnetization is evolving. This is that rho is nothing but a combination of Ix, Iy and Iz, three components of the angular momentum operator. It is combination and also because of the coefficients are also there. Rho of t at any given instant of time t is given by Ax of t into Ix plus Ay of t into Iz plus Az of t into Iz. It is a linear combination of these things. Ax, Ay and Az are just the coefficients, they are just the number. It defines the amount of Ix, Iy and Iz which is present at the rho t when you calculate. And this was, we correlated directly. It is nothing but Ix of t, Ax of t is nothing but Mx of t. Similarly, My of t is equal to Ay of t, and Mz of t is equal to Az of t. That's what we said. And I said, if I know rho of 0, that is the initial state of the beginning state of the density operator, then I can find out what is the density operator at the time t. For that, we have to follow certain norms. And I also said that everything in NMR we can treat as rotations. I take a simple pulse sequence, apply a radio frequency pulse, pulse is a rotation, and don't do anything after the pulse, keep quiet. A free precision, and a free precision is a rotation. The chemical shifts evolve in the delay. So delay is a free precision, and during the delay, of course, chemical shifts can evolve, that is a rotation. Couplings can evolve, that is a rotation. All these things can be treated as rotations for analyzing the pulse sequence. So I gave an expression rho of t, if I want to find out at a given instant of time t, is equal to e to the power of minus I h of t, where h is the Hamiltonian, t is the time, into rho of 0 into e to the power of I Hamiltonian h into t. So what it means is we have to construct a Hamiltonian. If you know the Hamiltonian, if I know rho 0, I can calculate rho of t. And I said if I apply a pulse along I axis, then it is a rotation about x axis, it is a rotation about x axis. If I apply a pulse about y axis, it is a rotation about y axis. Similarly, applying pulse about z axis, there is a rotation about z axis. Or if you don't do anything, free position, the rotation about z axis. And I also said for the Hamiltonian, if you apply a pulse along x axis, Hamiltonian can be written as Ix. And if you apply a RF pulse of power omega 1, the Hamiltonian for the x pulse when applied for x pulse is nothing but, I said omega into I of x. Omega is in the offset or the chemical shift. Similarly for Iy, it is omega into Iy. Hamiltonian is omega into Iy. For free precision Hamiltonian, omega is equal to, we said Iz into omega. Omega into Iz. Omega is again offset. This is what we understood. So we wanted to go further and see how we can evolve, how we can understand the product operators to find out the evolution of magnetization in different time periods of the sequence. First you must understand, now we will continuing further here, the operation of any given pulse sequence depends upon the time ordering of the pulses and the intervening periods of free precision. That is very important. Supposing I have a pulse, two pulse sequence, and there is a time delay here, and apply 90 pulse here and 90 pulse here. Now I have to see application of how what happened to the density operator, what are the rotations that is happening by application of 90 pulse, or whether it's x pulse or y pulse, and during this delay how the magnetization is evolving, what is happening to the free precision, whether the chemical shift is evolving or J coupling evolved, etc. Then you have to go for this, then you have to go. You cannot go in the random order, it is a time ordering. But one important thing I want to say is, during the intervening period between this, for example during this delay, if I want to find out how the chemical shift is changing, how they are evolving, or spin coupling is evolving. That can be interchanged. You can work out first chemical shift evolution and then J coupling evolution, no problem. But the time ordering of the pulse sequences have to be maintained between each of these blocks. Then we can work it out in the evolution of chemical shift, couplings, everything can be interchanged and you can work out the way independently. It can be free position, J couplings or chemical shift in any order you can do in this given block. But the entire sequence, the way in which you are operating, that should remain same. You cannot operate first here and then come back here. It should start from a sequence, but within this period, how, for example, when you apply here in this period, whether J coupling evolves you take first or chemical shift evolution you take first, doesn't matter. That order is immaterial. But sequence of the pulses, the time ordering, that has to be maintained. That is very important. So this is what I just wanted to tell you. With this idea, life becomes very simple for us, so that we can start understanding what is happening. And this happens, we can do only when the spin system is weakly coupled. As I said initially itself, this density of product formalism is applicable to weakly coupled spin system. So it doesn't matter here. So it is always weakly coupled. So it doesn't matter whether you take chemical shift or coupling evolution first or second. Another interesting thing you should understand, if I am applying a non-selective radio frequency pulse, hard pulse for a given system, let us I have two spins are there which are coupled or not coupled, no problem. Let us say it is coupled. If I take two spins which are coupled I and S, then I can break this into two cascade of pulses as if I am applying the pulse selectively once on S and once on S spin system. So it doesn't matter. I can break it into two operations. That means the effect of the pulse on I spin can be evaluated individually and the effect of the pulse on the S spin can be evaluated individually. So I can break down into cascade of two pulses and it can be independently acting on I spin and S spin. Then how do you evaluate whether I spin first or S spin first? Doesn't matter. Ordering does not matter, that is immaterial. But it can be broken into as if there are cascade of two pulses, first on I spin and one on I spin and one on S spin. Okay. And during the radio frequency pulse, the chemical shifts, coupling constant, everything you can assume to be switched off. That means you are applying RF pulse, then you are not talking about chemical shift and coupling evolution as evolution, that you consider as if it is switched off, nothing is happening to that. And you have to treat only about the rotation about a particular axis. That means I am applying a RF pulse and then delay and collect the signal. As when you are applying the RF pulse, all you have to worry about is rotation about a particular axis in which you are applying the pulse, X pulse or Y pulse, and the rotation about the plane we have to consider, that is all. During that time, do not worry about chemical shift or spin coupling constant. They can be assumed to be switched off or not. Right now you can imagine to be not there. So when you evaluating the effect of radio frequency pulse, you can, that means you can ignore. Temporarily you can think of switching off. And only the rotation of the XY plane has to be considered. That is what I wanted to repeat. Now with this knowledge, what we gain, let us understand or analyze what happens or how the magnetization evolves under free precession. What is free precession? During a delay. Just give a delay and if there is a rotation going on about Z axis. The spins are undergoing rotation about Z axis. Now let us see when the magnetization is along Z axis, rotation is along Z axis, how we can understand the evolution of the magnetization in this sequence. Now the spins undergo precession in a static magnetic field. Simply put the sample in a magnetic field, spins undergo precession. What is that precession? It is a free precession. And the rotation is about Z axis. As I said, omega is the offset, that is the chemical shift, about Z axis, and Iz is the operator for that. Okay. Now omega is offset, I said. Start with the magnetization along Z axis. Initially, you have put this sample, there is a free precession Hamiltonian is omega into Iz. Now start with the magnetization along X axis. Assume now magnetization is along X axis. Okay. So that means you have brought the magnetization to x axis somehow. That means at time t is equal to 0, we have only Ix. Rho 0 is equal to Ix. Okay, rho 0 is equal to Ix is my initial Hamiltonian, beginning Hamiltonian. Rho 0 is equal to Ix. And let us say I am applying a hard pulse along x. Hard pulse, as I said, omega 1 is the RF power, and the x pulse Hamiltonian can be written as omega 1 into I of x. Omega 1 is the RF field strength. Okay. So with this idea, let us see what is going to happen. Allow the spins to precess. As I told you, the precession is along z axis, for which Hamiltonian is omega into Iz. Now what do we have to do? We have to solve the equation rho of t to get what is the final density operator at time t. We should know what is rho 0. We should know e to the power of minus what is the Hamiltonian h, and of course time is t is the time. We know what is rho of 0. What is rho of 0? Rho of 0, as I said, is Ix. We are applying the pulse along x axis. Okay. When you are applying the pulse along x axis, what is the Hamiltonian, free precession Hamiltonian? Rho of t into Iz. So I know h now, I know rho of 0. Simply plug it in, substitute, and then we have to evaluate it. If you substitute, it turns out to be rho of t equal to exponential minus I omega t into Iz, rho of 0, exponential omega t Iz. Sorry, I have missed I here. I should be there. Please remember, I should be there. It is typo. There is a typo. I should be there. So exponential minus I omega t Iz, rho 0, exponential I omega t Iz. This is what I have to evaluate now, so that I can get rho of t. How easy or difficult to evaluate this? But one thing, when you are evaluating, you have to evaluate in the same order. You cannot bring this one here or this one here. Not allowed. You cannot swap the terms. You cannot interchange the terms. The order has to be maintained while solving. And how do you solve such type of equations? And the good part of it is many stalwarts researchers who have done this work, stalwarts of NMR and others, already they have worked out. And of course, solution for such type of equations is known right from the beginning. We don't have to worry. We have to simply use the trigonometric identity. What is the trigonometric identity for such type of thing? Exponential I e to the power of minus I theta Iz into Ix of exponential I theta Iz. If I use this trigonometry, this can be broken down into cos theta of Ix plus sin theta of Iy. This is a simple trigonometric identity. Okay, it is already known. You don't have to worry about it. Now with this, knowing this one, put theta is equal to sigma t. Now instead of theta, I have to put sigma t. Again, I is missing. I'm sorry, while cutting and pasting this has happened. So now rho of t is equal to exponential minus I omega t Iz, Ix, exponential I into omega t Iz. This can be equated using this identity as cos of omega t Ix plus sin of omega t Iy. We just use this trigonometric identity for this type of equation. So that means you don't have to go to the elaborate analysis of such type of this thing to find the expression, to find the solution. It is very well known. Simply use the well known trigonometric identity. If you remember, e to the power of minus of I theta or I omega t Iz, Ix exponential I omega t Iz can be written as cos omega t into Ix plus sin omega t into Iy. I have simply plugged in the trigonometric identity. That is all. Now after the time t, the density operator has become this now. So this is nothing but rho of t now. This is what we have to solve. We knew rho 0, we know what is Hamiltonian, we substituted, and then the solution for this is using the trigonometric identity, we got this one. So after the time t, the density operator has now become cos omega of t into Ix plus sin omega of t into Iy. So we know what is the percentage of Ix, what is the percentage of Iy present, amount of Ix and Iy present here. Okay. It means what is happening is magnetization which was along x axis with the time has undergone rotation with the time t. As time is increasing or time is changing, the magnetization has undergone rotation in the xy plane and developed ix and iy components, which is oscillating. Cosine and sine function, they are oscillating functions. So, it has developed oscillating ix and iy components. This is what it means in the free precession. What we understood is, we know free precession Hamiltonian is, what is the free precession Hamiltonian we understood? It is nothing but Iz into omega. What is omega is the offset, and of course we applied a pulse along I axis, and then we know that is what is rho of 0. Rho of 0 is equal to Ix now, because pulse is applied along x axis, and then we know the Hamiltonian, we just plugged in, use the trigonometrical identity, we found out what is rho of t as a function of time, and we know the magnetization which was along x axis as a function of time has undergone rotation and developed oscillating Ix and Iy components. So, all these operations can be represented by a simple notation. What is that notation? Is called a arrow notation. In all the books you see, and all the when you try to understand product operators in various books and the literature, you will see it is represented by an arrow like this. That means if rho of 0 is there, that is the beginning of my density operator. My Hamiltonian is h and t. For that, during the period when there is a Hamiltonian ht, when this is operated on this rho 0, and the final Hamiltonian, final density operator is rho of t. What it means is, if I know rho of 0, if I have h of t, which is written on the arrow, means this is my Hamiltonian, and it is operating on this rho of 0, and finally I get rho of t. That is what it is. It should be understood. So, for free precession, if I want to write it, I know rho 0, that was my beginning Hamiltonian, beginning density operator. Now, my rho t into Iz is my Hamiltonian for free precession. So, this is acting on that. The free precession rotation, what is going on? The rotation about z axis is going on, and this is what is rho 0, and finally using the trigonometrical identity we got cos omega t into Ix plus sin omega t into Iy. Now, both rho and h are written in terms of Ix, Iy and Iz. That is what we are going to do. Hamiltonian, both rho and h is always written in terms of Ix, Iy and Iz, which tells you the amount of Ix present, Iy present, Iz present at for rho of t. So, in general, what it means is, if you want to solve equations of this type, for let us say rho of 0, if h of omega t Iz is operating on rho of 0, to get rho of t, this is an expression which is generally given like this, is exponential minus I of Ia, Ib, exponential I of Ia of t. Now, what does it mean? Ia and Ib can be any axis, on any axis, x, y and z, no problem, and solution for such equations are well known. It is generally, in general, solving a general equation of the type. Any of the, in the product operator analysis, if you try to do, either for the free precession, when you apply RF pulse or chemical shift evolution or J evolution, you always come across an equation of this type, for which you have to find a solution. This solution, you can, in generally, for an equation can be written like this: exponential I minus I of Ia into t, Ib, exponential I of Ia into t. So, for solution we got for Ix and Iz, for during free precession we know. We worked out, and we using trigonometric identity, we wrote it as cos of omega t plus sin of omega t. We worked that out. That you remember this one here. Cos omega t Ix plus sin omega t Iy. Ix and Iy component generated. But it is not all the time like that. It depends upon in which axis you are applying the pulse and which is your Hamiltonian. And that is, it depends upon what is your Hamiltonian and what is the axis in which you are rotating. Okay, that is very important. So, it is a general equation. For all such equations, The solutions are very well known. All such equations solutions are very well known. You don't need to make explicit calculations. Using trigonometric identities, they have been tabulated. And this is a simple table which tells you what is the rotation about an axis, what is an operator, and what is the identity, what is the final solution for such type of things. Only couple of them is needed for you, because let us say you can have an operator Iy or an operator Iz. What can happen for Iy and Iz? You can have a rotation of about x axis or rotation about this. Iz can rotate. You can have Iz rotation about of Iz about x axis. You can rotate Iy about x axis. No problem. You can take Ix. Ix is an operator that can rotate about y axis. Iz is an operator that can rotate about y axis. Similarly, Ix and Iy operators can rotate about z axis. There are various combinations you can think of. So, as a for all these things, identities are very well known. For example, I will take the first one. For an operator Iy which is rotated about axis x. This is what is written. This is operator Iy and it is rotated about an axis. See, remember general expression which we wrote in the form of Ia and Ib. Please understand, this is an operator that is to be rotated. That is the operator which undergoes rotation. And the axis of rotation is given by this. This is all what is there in all the thing what we do in the product operator formalism. When we try to work out, this is what you should understand. An expression of this type you have to understand like this. If I consider this thing, this is an operator that is undergoing rotation, that, and this is axis of rotation. That means Iz is rotated about x axis. That is what it implies. If I consider an example of this, it is already written here. See, for example, if I consider second row and third row. What is the second row here? Second row says this thing, rotation of Iz about x axis. I am sorry, this is second row. Third row. Third row is rotation of Iz about x axis. Here rotation of Iy about x axis. That is all you have to understand. Finally, you write a big equation like this. Physically it means it is a rotation of an operator about a particular axis. Simply in this case example, this is the rotation of the operator Iy about the axis z. And for all these operations 5 or 6 which are there, solutions are easily written like this. For rotation of Iy about x, it is the solution, cosine of theta Iy plus sin theta of Iz. Similarly, for rotation of Ix about y axis, it is cosine of Ix minus sin of Iz. Similarly, take Ix, rotation of Ix about z axis is given by cosine of theta of Ix sin theta. The amount by which it is rotated is given by theta. Okay, that is what it is. So, simply theta is the amount by which you are rotating, and this is the axis of rotation. This is the operator that you are rotating. That is all you have to understand. For 6 of them, this equation is very well known, solution is known. You must remember these things. If you know these things, you can understand the operation and the rotation of any operator and any axis in any pulse sequence given. You can easily do these things. Okay. Now, you may ask me here, when we discuss this thing, one interesting thing you notice, we always started asking, writing about rotation of Ix, Iy. See, for example, Ix, Iy operators are rotated about x, Ix, Iz rotated about y, Ix, Iz, Iy rotated about z. But we never found out what happens about the rotation of Iz about z, x about x and y about y. That is also possible. Here you have seen rotation of Iy and Iz about x, rotation of Ix and Iz about y, Ix, Iy about z. But we have not asked rotation of Iz about z, rotation of Ix about x, Iy about y. What happens to those rotations? Because other rotations have been given, solutions are very well known in the table. Simply you write like this, rho of t is rotation of Iz about z. That is what it implies. That is what we were trying to understand. This is exactly equal to Iz if you work out. That means Similarly, you work out, I will come to that what it is. Similarly, you work out for rho of t, rotation of ix about ix, rotation of iy about iy is equal to iy. What does it mean? It means all these three rotations have no effect. This has no influence in your when you are making the analysis. That means rotation of z magnetization about z, x magnetization about x, and y magnetization about y has no effect at all. Please understand, rotation of z about z, x about x, and y about y has no effect. Only rotation of z about x and y, rotation of x about y and z, as other thing y and z, or rotation of y about x and z, they are important. Okay, not about rotation of the same operator iz about z, ix about x, iy about y have no effect, and you don't have to worry about those things when you are analyzing any pulse sequence. So, what happens in the free precision if you apply an 90-degree y pulse instead of a x pulse? You are understanding, we apply a pulse along x axis, wrote Hamiltonian as h of x is equal to omega 1 into I of x we wrote. Remember, omega 1 is the RF power and Ix is the Hamiltonian along Ix, that is what we wrote, right. So, h for the free we know omega into Iz, and then hard pulse along y axis we are applying Hamiltonian is Iy. Instead of Ix it is Iy, there is no difference. So, for the Hamiltonian for the hard pulse you have to write as omega 1 into Iy. Instead of omega 1 Ix it become omega 1 into Iy. Now, at time t is equal to 0, the pulse is applied along y axis, that means rho of 0 is equal to Iy. Earlier it was rho of 0 is equal to Ix because pulse was applied along x axis. Now you are applying pulse along y axis. So, rho of 0 is equal to Iy. So, what you have to do now? You have to solve this equation same. Now, what is rho 0? What is the operator and what is the operator in which you are rotating? You should know by now. This is the operator that is rotated about z axis, because free precision rotation is about z axis. This is the operator that you are rotating. Now, Iy is rotating because you are applying the pulse along y. Iy operator is rotated about z axis. So, what you have to do? Go back to your table here. Iy rotated about z axis. Simple. This should be the solution. Simply write down those equations for this now. After the time t, the density operator is simply written by this. What I did is I copied from the table, that is all. The solution is known. What you have to understand is the operator that which are rotating, which is rho 0 or whatever it came at the center of that expression, and e to the power of I into h into t, where Hamiltonian was the operator, the axis in which you are rotating. If you know these two, then from the table which is given, you can simply write the solution without going into any explicit calculations at all. So, when we apply RF pulse along y axis for a free precision, we know rho of t turns out to be this one. So, that means the magnetization along y has undergone rotation and developed oscillating Ix and Iy components. There was a magnetization along y axis, it has undergone rotation and developed Ix and Iy components. That is what it means. Same, when it was magnetization was along x also, it started moving and then developed Ix and Iy components, oscillatory components. Same thing here also, the cosine and sine components will be developed now. Now, with this we have to introduce few other things, what is called rotation of operators under 90 and 180 pulses. This is basically very important. All what is written in the table solution can be understood by this method also. This is also another same approach, it is in a simple form written there. But to make it clear for you, I will tell you all those things which you know already. We have discussed this when we discuss about the evolution of pulse phase, receiver phase and rotation, everything. We discuss this thing. But again, let us see rotation operators under 90 and 180 pulse, how it happens. I will see effect of pi by 2 pulse on product operators. What is a pi by 2 pulse? Now it is a omega type pp is pi by 2 RF pulse. Omega is, you know, the pulse width is always given by gamma h1 into Tp. Gamma h1 is equal to omega 1, Tp is the pulse width, and which is equal to pi by 2. And when cos equal to pi by 2, when cos pi by 2 is 0, because cos 90 is 0. Okay. Similarly, sin pi by 2 is 1. You know that one. Okay. Now we will understand. When I apply a pi by 2 pulse, that is x pulse, on Iz, what will happen? It will go to the product operator Iz will become minus Iy. Apply a pi by 2 pulse, pi by 2 x pulse, Ix on x axis, you apply a pulse, then Iz will become go to minus Iy. Similarly, apply plus Iy pulse, Iz will go to Ix. You can also apply in the opposite direction, other axis. Instead of plus x, I apply along minus x, then Iz will go to Iy, here Iz will go to minus Ix. Very simple. This we have been discussing, we understood by vectorial diagram also about the pulse phase, receiver phase, how it is rotating, everything, you know, different pulses when we apply, how the magnetization is undergoing rotation, we understood that. Similarly, if I have a Iy pulse, Iy magnetization, let us say, I apply a Ix pulse, then product operator Iy will go to Iz. Similarly, Iy on Iy remains Iy. What does it mean? It has no effect. I tell you, you apply a pulse along the same axis, you simply rotate along the same axis. This has no effect. Okay. So, pulse has to be applied in the other axis, different other two axes. Okay. Now, if you want to see Iy, effect of Iy, the pulse has to be on x or z, not on Iy. So, Iy pulse applying on Iy has no effect, that is what we said. It remains same, there has no effect. Rotation of Iz about Iz, this what it essentially means is, here it means it is the rotation of Iy about Iy. Rotation of Iy about Iy has no effect. Similarly, rotation of Iz about Iz has no effect. So, here again apply Iy minus Ix pulse will take up the product operator goes to minus Iz. Similarly, Iy product operator, when you apply minus Iy, minus y pulse, it goes to Iy. So, all these things, you know, Ix operating on Ix has no effect, and when you apply a minus y pulse on Ix, it goes to minus Iz. The rotation about Iy, Ix will go to Iz. Rotation about minus Ix, Ix will go to Ix. This is how you have to understand. Rotation about Iy, Ix will go to Iz. These are all simple effect of the pi by 2 pulse on various product operators. All these are product operators. Effect of pi by 2 on all the product operators, if you know, if you remember these things, any pulse sequence you can very easily understand product operators, and you understand, they analyze these things using product operator any pulse sequence and see how the magnetization is evolving at different time periods of the sequence. We can also talk about effect of pi pulse on the product operators. So far in the previous slide we saw about the effect of pi by 2 pulse. We can also discuss about the effect of pi pulse. We know that what is omega 1 Tp is equal to pi, cos pi is equal to 1 minus 1 and sin pi is equal to 0. It is very simple. When you apply, when you rotate about Ix, I apply a 90 pulse, pi pulse Ix on the, along x axis, then Iy will go to minus Iy. It is simply inverse the magnetization, you know that. A 180 pulse will tilt it in the opposite direction. Similarly, Iz will go to minus Iz if you apply x pulse. If you apply y pulse, Ix will go to minus Ix. If you apply Iy pulse, y pulse, Iz will go to minus Iz. If all these pulses are pi pulses. Okay. And the effect of the evolution of operator, this is taken from the Freeman book, Ray Freeman's book. It is a very good book and fantastic book to read and understand. The effect of evolution operators acting on any one of the operators describe the state of the spin system can be given like this. So, what it says, evolution operator is given in the top row, and then what is the state of the spin system is given by what is given here in the column. For example, I will say I apply Ix pulse on Iy, it goes to Iz. Apply Ix pulse on Iz, it will go to minus Iy. For example, I will take Iy pulse, apply on Sy, another spin, has no effect. I told you You can if you apply pulse on I spin, S spin will not be disturbed. You can independently evaluate application of the pulse on I spin, application of the pulse on the S spin independently. So like this, all these things we can discuss. These are all, what are these two? This is the longitudinal Z magnetism, everything we will discuss when you go further. But this is the basically, it tells you evolution of this operator, each of this operator, and when you and how you describe the state of the operator when these things evolves is given like this. So when Sx operates on Sy, okay, we give rise to S that. Like this, the table has to be utilized. So with this, now we will come back, and since the time is up, we will discuss about the rotation operators, everything later stage in the next class. In this, what I was trying to say is, we after understanding something about the product operators, some fundamentals concepts, we wanted to understand what happens to the free precision. We wrote down the free precision in Hamiltonian H of free. Hamiltonian free precision is equal to omega into Iz, because during free precision, which is during delay, magnetization rotates about Z axis. So Hamiltonian is omega into Iz. Omega is the offset, I think the rotating frame or chemical sheet, what you call. And then apply a pulse along I axis is rotation about X axis. Apply pulse along Y axis, rotation about Y axis. And then how these things evolve is given by a simple expression, e to the power of minus IH into T into rho of 0, e to the power of IHT. Okay, this now rho of 0 is the initial state of the product operator. If you know the initial state, you know the initial state of the density operator, you know what is the final state of the density operator, rho of T. All you have to understand is you have to build the Hamiltonian. You should know rho 0, and then you can find out rho T. So we gave simple expression. Rho 0 is nothing but the operator that is to be rotated, and then what e to the power of IHT, if I write down the Hamiltonian, they all can be expressed in terms of rho 0 and rho T in terms of Ix, Iy, Iz components. That is what I said. So if I say rho 0 is Ix, that is the operator that is being rotated, and then in the Hamiltonian you will write Ix, Iy, Iz, whatever it is, and that tells you the axis in which it is going to be rotated. For all these things, solutions are well known, and then if using a simple trigonometric identity, they have been tabulated. You can simply look into the table and write down. Or in other words, I also gave the table where we can say what is the effect of different pi by 2 pulses on different product operators. What will happen if I apply pi by 2 x pulse on Iz, Ix, Iy and all those things. We discuss that. Similarly, effect of pi pulse. So with all those things, now it is very easy for us to analyze any pulse sequence. In a sequentially we have to go first pulse, then effect of the pulse, and then the delay. What will happen, whether chemical shift evolves, pre-precision rotation, J coupling is evolving, everything can be treated as a rotation, and it has to go sequentially in the pulse sequence. And in a given block, for example, there is a delay. In that, chemical shift may be evolving, J coupling also may be evolving. Both you can operate either first coupling and then chemical shift later, does not matter. That is immaterial. But in the sequence, in the pulse sequence has to be followed. Then at the end you can find out what is the rho of T, final density operator at the time T. So that is how we can understand the state of the magnetization. We will go further, I will stop at this stage, we will come back in the next class, continue further and try to analyze some of the sequences. Thank you.